In the previous video, we looked at the first isomorphism theorem and some examples of it. So I'm going to, before continuing today, I will recall for you what is the first isomorphism theorem. What is the first isomorphism theorem? It says that if let phi from G to G prime be a group homomorphism. In this case, then we have an isomorphism from G mod kernel phi to image of phi, right? So this is the statement of first isomorphism theorem. It says that if you go modulo the kernel, you get a group that is isomorphic to the image group. Remember, kernel is always a normal subgroup, so G mod kernel phi has a group structure. It is isomorphic to the image of the group, image of the homomorphism. So image of phi is a subgroup of G prime. Okay, and we saw one example of this. We saw that if G is a cyclic group of order n, G is a cyclic group containing n elements, then we saw that G is isomorphic to Z mod nz. So any cyclic group is of the form Z mod nz, and this was an immediate corollary of the first isomorphism theorem, because we look at the homomorphisms from the integers to the group G, sending 1 to the generator of the group G. So then kernel will be precisely nz. It is an onto map, so there will be an isomorphism like this. Let's look at another example of first isomorphism theorem. So recall that C star is the group of non-zero complex numbers with multiplication. These form a group under multiplication, and let's denote R plus to be positive real numbers also with multiplication. So we saw in previous videos that these are groups under multiplication. Consider the map. Consider the function, let's say phi from C star to R plus, which sends a complex number to its absolute value. So if you recall, absolute value is simply this function. A plus IB is a complex number, so A and B are real numbers. I is the square root of A square root of minus 1. You send it to A squared plus B squared. That is this function. Absolute value of A plus IB is A squared plus B squared. So in order to see what the first isomorphism theorem has to say about this, let's look at the kernel of this map. So what is kernel phi? So kernel phi is by definition complex numbers with absolute value 1. Okay, so if you represent complex numbers in the plane, so this is the R real axis and this is the imaginary axis, right? So this is the kernel phi. Kernel phi is simply the unit circle denoted by S1. So this is the set of elements, complex numbers, which have absolute value 1, the unit circle around the origin. That is a kernel phi. What is the image of phi? So image, remember, phi is a function from C star to R plus, positive real numbers. If R is a positive real number, then absolute value of R is simply R. So phi is actually onto. In other words, image of phi is all of R plus. So what is the first isomorphism now say? First isomorphism theorem gives C star mod S1 is isomorphic to R plus. Okay, so the first isomorphism says C star mod S1 is R plus. Okay, so you should spend some time to think about this example, and this will hopefully help you with understanding quotient groups. So this as group, so C star mod S1 is the set of left cosets, right? What are left cosets? These are, so this are left cosets of S1 in C star. So these are of the form Z S1 Z in C star. That's simply the set, right? And on this there is a group structure. Remember, of course, that C star is an abelian group, so every subgroup is normal. And in any case, S1 is a kernel of a group homomorphism, so it's normal. So think of this, the group C star mod S1, as it is the left cosets of S1, but think of them as circles of varying radii. Okay, so you have a radius 1 circle, that is S1, radius 2 circle, radius 3 circle, radius 1.3 circle. So, and if you think about this, if you take all such circles, the radius will be a positive real number. So you take all circles of positive radius, the cosets can be represented by those positive reals, and hence we have an isomorphism like this. Because if you have all cosets, they are represented by simply the radius, because cosets are simply circles of different radius. So and they are represented by positive real numbers. So that is a slightly intuitive explanation of this isomorphism. Okay, one more example let's do. This is something that you have seen before. Remember, GLNR is the group of invertible n by n real matrices. Consider the map from GLNR to R star, non-zero real, the determinant map. So a matrix A goes to determinant of A. Because A is invertible, determinant of A is non-zero and it's a real number. So it's in R star, and it's certainly a group homomorphism that we have remarked earlier. Dit is clearly onto also, right? Because you take any real number, positive non-zero real number, you can construct a matrix with that determinant. For example, you can just take a diagonal matrix with that number being that one of the entries and all other diagonal entries being 1. So this is easily seen to be onto. What is the kernel of determinant? This is the group of matrices in GLNR which have determinant 1. We call this SLNR in an earlier video. So first isomorphism theorem gives GLNR mod SLNR is isomorphic to R star. Okay, so this is also a consequence of first isomorphism theorem. So in general, if you want to prove statements about quotient groups or solve problems involving quotient groups and isomorphisms involving quotient groups, immediately you should think of first isomorphism theorem and the other two isomorphism theorems that I will do later in this video. One remark I will make before I continue with second isomorphism theorem. Let's say that G to G prime is a group homomorphism. Then G mod kernel of phi is isomorphic to a subgroup I mean, this is exactly the statement of, this is an immediate consequence of the first isomorphism theorem, because first isomorphism theorem says G mod kernel phi is isomorphic to the image of phi, which is certainly a subgroup of G prime. So G mod kernel phi is isomorphic to a subgroup of G prime, and hence G mod kernel phi, I will write it like this, can be identified with a subgroup of G prime. So it is for all practical purposes a subgroup of G prime. So we usually think of G mod kernel phi as simply a subgroup of G prime. Okay, so sometimes it's useful to think of G mod kernel of phi as a subgroup of G prime. In particular, if kernel of phi is just E, which is to say phi is 1 1, right? Kernel phi is identity only if and only if phi is 1 1, then G can be thought of as a subgroup of G prime. If G to G prime is a one-to-one group homomorphism, that means it's injective. G naturally is thought of as a subgroup because its image is isomorphic to G by the first isomorphism theorem, and we can replace G by its image and think of G itself as a subgroup of G prime. Okay, so now that we have looked at various examples and a remark about first isomorphism theorem, let's go ahead and do the remaining two isomorphism theorems. So the second isomorphism theorem says the following: let G be a group, okay, I am going to consider two subgroups of G. Okay, let H and N be two subgroups of G. Assume that N is normal in G. Okay, so I am not assuming anything about H other than that it's a subgroup, but I am assuming that N is actually normal subgroup of G. Then the second isomorphism theorem says that H intersection N, okay, so it says several things. So let me, maybe I should write them as separate statements. Then H intersection N is a normal subgroup of H. So H intersection N is a normal subgroup of H. N, so the product set Hn is a subgroup of G, and N is a normal subgroup of Hn. And finally, in 3 we have H intersection H modulo H modulo H intersection N. By 1, H intersection N is a normal subgroup of H, so this is a group. By 2, N is a normal subgroup of Hn, so I can consider this. Okay, so H mod H intersection N is same as Hn mod N. Whenever you see in books statement about second isomorphism theorem, this is what we usually refer to as second isomorphism theorem. The statements 1 and 2 I wrote here are simply needed to make sense of the third statement, right? Because H intersection N, it needs to be a normal subgroup of H to talk about the left hand side group. Similarly, Hn needs to be a group and N needs to be a normal subgroup of Hn in order to make sense of right hand side as a group. So this is again group isomorphism. I have been using this symbol to always denote group isomorphism. Okay, so let's prove this quickly. It's not difficult at all. Okay, so statement 1, we know that H intersection N. So what is the meaning? So certainly H intersection N is contained in H. It's a subgroup obviously, because H intersection N being a intersection of groups, it is a subgroup. This is very easy exercise because identity is in H and in N, so it's in H intersection N. If two things are in the intersection, they are both in H, so their product is in H. They are both in N, so their product is in N, so their intersection is in their product is also in the intersection. So this is a very easy exercise. In order to check that it's a normal subgroup, what do we have to check? So let us choose H in capital H and N in H intersection N. Okay, so this is we need to check that. We need to check that H N H inverse is in H intersection N. Right, because this is the definition of a normal subgroup. So recall, we say that H is normal in G. Definition: if G is in G, H is in H, then GH G inverse is in H. So you take something from the bigger group and something from the smaller group and consider this element. It must be in the smaller group. Here we are interested in proving H intersection N is normal in H. So we have to take something from H, something from the smaller group, and consider this element and show that it's in the smaller group. Okay, first of all note that H and H inverse is in N because H is in G, N is in N, and N is normal in G. Right? So this is because N is normal in G, that is a hypothesis. So we are given that N is a normal subgroup of G. So you take something in H, then it's obviously in G because H is a subgroup of G. So small h is in the group G, small n is in group N, and the element Hn and H inverse will be in N. On the other hand, Hn H inverse is also in H because H is in H, N is in H intersection N, which is contained in H. So H is in H, N is in H, and H is a subgroup. Note that because H is a subgroup and small h is in it and small n is in it, small h, small n, small h inverse will be in H. So these two things together imply that H and H inverse is in H intersection N. So as we needed, so Hn, so 1 is proved because H intersection N is a normal subgroup of capital H. Let's prove 2. 2, remember, says two things, two statements are made in 2. It says that first of all it says that capital H times capital N is a subgroup of G and that capital N is a normal subgroup of capital Hn. So first of all, what is capital Hn? This I defined in an earlier video. Hn in general, for any two subsets of a group, the product is simply this set. You take elements from the first set and elements from the second set and multiply in that order. So you take small h from capital H, small n from capital N, and you multiply them and you vary small h and small n. Okay, so why is this? So this is certainly a subset of G. Why is this a subgroup of G? So it's important to note here that if you take two subsets, their product is certainly not in general a subgroup. In fact, even if you take two subgroups, their product is in general not a subgroup. However, if one of them happens to be normal, it is a subgroup. Okay, let's check one by one the required properties. E belongs to H and E belongs to N. Certainly that is because both of them are subgroups. So E times E is E, which is in Hn. Remember, in order to be a subgroup, capital Hn must contain the identity element, it must be closed under multiplication, it must be closed under taking inverses. We have checked that it is closed, it contains identity. Let's take now two elements of the set Hn. So H1N1, H2N2. Let's say these are two elements in Hn. We want to prove H1N1 times H2N2 is in capital Hn again. But here we have to use normality of capital N. So note that N is normal in G. This implies H2 inverse N1 H2 is in N, because H2 is an element of the group G, N1 is in capital N, so this element is in capital N. So say H2 inverse N1 H2 equal to some N3. It is equal to some element of capital N, call it N3. This gives me N1 H2 is H2 N3. So I am just simply multiplying by H2 on the left both sides. Now what is H1 N1 H2 N2? This is equal to, because I don't remember, because of associativity I don't need to be careful about putting brackets. N1 H2 is equal to H2 N3 by that calculation. So this is H2 N3 N2. This can be written as H1 H2 N3 N2. Now H1 H2 are in capital H, so this is in capital H, product is also in capital H. Similarly this is in capital N, so this is in Hn. So we have said that two things in capital Hn means that product is also in capital Hn. Finally, how do you show inverses? It's the same idea. If you have Hn in capital Hn, what is Hn inverse? This is N inverse H inverse. Okay, by what we have shown here, we have shown that N1 H2 is H2 N3. So here what we have really shown is that anything in N times anything in H is, you can switch the two, you can replace, you can bring H2 to the front, but on the right now there will be some other element of N. So this is by the same calculation as above, equal to H inverse times some N1 by the same calculation as above. Okay, and this is in capital Hn. So the point that I want to highlight here, and this is the point we used above, if N is normal in capital G, then H and for G in G, Gn is equal to Ng. See, N elements of N do not necessarily commute with a fixed element, but as a coset they commute. This is something that we have seen I think before also, but this is exactly the calculation that we have done here. So something in N times G is G times something else in N. So this is the point that I would like you to remember, and that's what we have used. So Hn is a subgroup of G. So this certainly proves a part of the second statement of the theorem. And also N is E times N is contained in Hn, right? Because Hn is products of elements of capital H times elements of capital N. E is an element of capital H, so you have this. So N is a subgroup. Okay, to finish the proof of statement 2 of the theorem, we want to show that N is actually normal in capital Hn. But that is obvious because N is certainly normal in Hn because N is normal in even a bigger group, namely G. See, what is the picture now? We have N sitting inside Hn, sitting inside G. N is normal in capital G, that means you take something in capital G, take something in capital N and do that operation G N G inverse, it's in capital N. For G in G, N in N. This is certainly going to hold if you take something in capital Hn and do this same operation. So, because Hn is already a subgroup of capital G. So, if you take something in capital Hn, it's in G, so this condition holds. So, if you have a subgroup which is normal in the ambient group G, then it will be normal in any other subgroup that contains it. So, this proves 2. Right, 2 is completely proved because 2 is the statement that Hn is a subgroup of G, which we have shown, and we also showed that N is a normal subgroup of Hn. So now let's finally prove the main part of the theorem, which is the isomorphism part of the isomorphism theorem. Now we want to show that here we will show. So just to recall, H mod H intersection N is isomorphic to Hn mod N. This is what we want to show. So let's consider, in order to do this, let's consider the map from H to Hn mod N. Let's call this phi. What is this map? Phi of a small h is by definition Hn. Okay, so this is the map. So I want to first of all understand what this really means. Remember that, so if you take what is Hn, so note what is Hn mod N. What is Hn mod N? These are all elements, all cosets. So note Hn mod N are the left cosets of N in capital Hn. So these are elements of the form An, where A is in capital Hn. So in general, this is the quotient, this quotient group An, where A is in Hn. But capital H is contained in Hn because of the, this is similar to in the previous part when we said N is contained in Hn. H is contained in Hn because identity is contained in N. So we can talk of Hn. So Hn belongs to Hn mod N if H belongs to H. Okay. So this is the explanation for this. I am sending H to Hn and keeping in mind that small h is also an element of capital Hn. So we want to claim that phi is onto and kernel of phi is H intersection N. Once we prove the claim, the theorem will follow immediately from the first isomorphism theorem. So what is the proof of the claim? So why is phi onto? So in order to prove phi is onto, we want to show that anything in the right hand side is the image of something. So let An be an element of Hn. So A is inside Hn, right? So A is an element of Hn, right? it's a left coset of capital N in capital Hn. So A is an element of Hn. So write A as small h times small n, where of course small h is in capital H, small n is in capital N. Now let's look at what is An. An is Hn n. So this can be written as Hn. But what is Nn? Because n is in capital N, Nn is just Hn. So An is equal to small h times capital N. But this, remember, is phi h. So we have started with an arbitrary element of Hn mod n and showed that it is the image of something in capital H. So this implies phi is onto. Right? So phi is onto. This much is okay. What is the kernel of phi? Kernel of phi is all elements of the group H such that Hn, so phi, the definition is phi of H must be the identity element. What is the identity element of Hn mod n? Hn mod n is the quotient group. The identity element is simply E times n. So this is the kernel, but this is equal to all elements small h such that Hn equals n. Right? En is equal to n. So I'm going to write it as things that map to n are the elements in the kernel. But what is Hn equal to n mean? So if Hn equal to n, I claim this is true if and only if H is in n. Right? This we have seen when we discussed cosets. Hn equals n if and only if H is in n. Certainly so, because if H is in n, then Hn and n have something in common, so they must be identical. Any two cosets are either identical or disjoint. So if H is in n as well as H is in Hn, because H is H times identity. So they are identical cosets. On the other hand, if Hn is equal to n, certainly H will be in n because H is in Hn. Okay, so this implies kernel phi. So these are elements, so I'm going to write it simply here, H in H such that H is in n. But what is this set? This is nothing but things that are in H as well as in n. So kernel of phi is simply H intersection n. So the claim is proved. The claim that phi is onto and kernel phi is H intersection n. Now the first isomorphism theorem says, so phi is a map from H to Hn mod n. Phi is onto kernel phi is H intersection n. So by the first isomorphism theorem, first isomorphism theorem applies to any group homomorphism. It says that G mod kernel is isomorphic to image. So in this case, image is all of this Hn mod Hn n, and kernel is H mod n, H intersection n. So quotiented by H intersection n is isomorphic to H mod the kernel, which is H intersection n, is isomorphic to the image, which is all of Hn mod n. Remember, this is the theorem that we wanted to prove. The second isomorphism theorem says H mod H intersection n is isomorphic to Hn mod n, and we have completed the proof of the theorem. Okay, so this finishes the proof. Okay, so let me stop the video here. In this video we've looked at some more examples of the first isomorphism theorem, and we've stated and proved the second isomorphism theorem. In the next video I will do the third isomorphism theorem. Thank you.